For the longest time, I feel like building cloud architecture was, well, it was a lot like traditional city planning.
Oh, absolutely. Yeah, very deterministic.
Right. You had your zoning laws, which were, your strict IAM policies, and you laid down your roads, which were basically your network topographies, your VPC peerings, all of that.
Right. And you could just draw the diagram, provision the Terraform modules,
Yeah.
and the system did exactly what you told it to do. It was a completely closed loop.
Yeah, exactly. As an architect, you could essentially stand on a hill, look down at the static grid you build, and mathematically predict exactly how the data traffic was going to flow. But, the moment you introduce autonomous AI agents into that environment,
It all changes?
it totally changes. That static city grid turns into this living biological organism. It starts like mutating in real time.
Yeah, the traffic isn't just flowing down those predefined roads anymore.
Yeah.
The applications are actively rerouting themselves.
They're building their own bridges. And in some cases, negotiating their own API toll booths without any human oversight whatsoever.
Which is wild. The blueprints we relied on even just, a year ago are rapidly becoming completely obsolete. The fundamental physics of how cloud resources are consumed and secured and billed, it's all changing at machine speeds now.
And mapping out that mutation is exactly our mission for today. So, welcome to this deep dive, everyone. To build today's architectural teardown, we synthesized a massive stack of live, verifiable public sources. And just a quick note up front, we processed and structured all of this using Gemini Notebook, but, we did that because we need hard, objective data to understand what's actually happening out there. Every single detail we're discussing is based on real public sources.
Right, because we're witnessing this rapid, massive collision of autonomous AI agents with core cloud infrastructure.
Yeah, the era of humans manually managing cloud environments is basically ending. So today we're unpacking exactly how to architect, secure, and pay for the machine identities that are taking our place.
We really have to stop thinking of these agents as just, mere software deployments. We're essentially deploying synthetic employees.
Synthetic employees, that's a great way to put it.
Yeah, and they consume resources like a massive, highly uncoordinated engineering department.
Well, let's unpack the sheer scale of that consumption, right? Because you really can't understand why the infrastructure is changing so fast until you look at the cost of the automation that's driving it.
Right, the API burn.
Exactly. Like, I was looking at Anthropic's unreleased cloud orchestration, and it completely redefines resource burn. So they set up 60 subagents.
Wow, 60?
Yeah, 60. And they gave them this collaborative workspace, right? And they tasked them with improving the known lower bound for the Riemann zeta function.
Which, just for context, is a notoriously brutal mathematical threshold.
Yeah.
Solving it isn't just running a calculator. It requires serious hypothesis generation, testing, and formal verification.
And they actually did it.
Wait, they actually improved it?
They did. They improved the lower bound from 41.6% to 67.2%. But, let's look at the mechanical orchestration required to actually achieve that. Those 60 agents autonomously ran over 2,400 shell commands.
That is wild.
Right. They wrote and executed their own Python numerical checks and ultimately produced this mathematically verified formal Lean proof. But the infrastructure cost, this is where my jaw just hit the floor. It took 31 million output tokens to execute that single task.
31 million tokens. That is a staggering amount of compute for a single mathematical proof.
I know. It's like leaving all the lights, the elevators, and the air conditioning on in a 50-story skyscraper over a 4-day weekend, all just to keep one single laptop powered on in the lobby.
That is a perfect analogy, yeah. The energy draw is entirely disproportionate to the localized output.
Exactly. It really begs the question, are we actually innovating, or are we just swapping expensive human engineering salaries for entirely out-of-control API burn rates?
Honestly, if an enterprise just tries to lift and shift these recursive agentic workflows into their existing API building structure, they will bankrupt their cloud budget in a week. Full stop. But the thing is, the vendor ecosystem sees this wall approaching. They know multi-agent loops are the future, so they're aggressively manipulating the underlying mechanics of their models to drive costs down. Like, take Google launching Gemini 3.7 Flash into general availability.
Oh, yeah. They introduced adjustable reasoning levels alongside, a massive 50% API price cut.
Exactly, 50%. And that adjustable reasoning is really the key mechanism there, because instead of forcing the model to run through its deepest, most computationally expensive neural pathways for just every basic classification task.
You can dial it back.
Right. The API allows the orchestration layer to dynamically dial down the reasoning depth. So you use cheap, shallow processing for a sub-agent that's, I don't know, merely routing a ticket.
And then you save the heavy compute for the big stuff.
Yeah, you reserve those heavy, expensive compute cycles strictly for the final mathematical synthesis.
Which makes sense. And Microsoft is playing the exact same volumetric game, right? They dropped MAI Code 1.1 Flash natively into GitHub Copilot.
Oh, right, and they slashed the price by 75%, didn't they?
Yeah, down to like 20 cents per million input tokens. Plus, they added integrated vision capabilities. So now, the local model isn't just reading text. It's literally ingesting complex system architecture diagrams and UI mockups straight out of the developer's IDE.
See, that structurally changes the economics of background refactoring. Because at 20 cents a million tokens, you can actually afford to have a CLI agent loop constantly running in the background across a 500-person engineering team.
Just actively reviewing code against visual architectural diagrams all day.
Exactly.
But wait, I mean, token price drops don't actually solve the core enterprise billing issue. Like, who cares if the token is 75% cheaper if you have a shared execution role and you have absolutely no idea which tenant in your multi-tenant application is burning through those tokens?
Right, the old chargeback black hole.
Yeah. So how are the cloud providers actually fixing that?
Well, that is the exact problem AWS is trying to patch right now with Bedrock. So they just extended granular IAM principal cost allocation directly to Bedrock Mantle endpoints.
Okay, meaning you can finally map specific LLM API calls directly to the calling identity roles inside AWS Cost Explorer.
Yes, but, and this is a big but, there is a massive architectural trap here. This new billing visibility is completely useless if your application IAM roles aren't strictly scoped per workload.
Oh, I see what you're saying.
Yeah, think about how many engineering teams deploy just a single generic execution role across their entire multi-tenant LLM application, just to save on deployment complexity.
Because it's easier, yeah.
Exactly. But if you do that, Cost Explorer will just show one generic role burning millions of tokens. You still have absolutely no idea which specific agent or customer triggered the burn.
Wow. Okay, so if you can't get granular visibility into your cloud API costs, or, if your compliance team is just terrified of sending proprietary data up to a central model, the natural instinct from architect is to pull the brain out of the public cloud entirely.
Pull it to the edge, exactly.
Right. You push the workloads to the edge, or you lock them down in highly regulated regional data centers. And Mistral is making a very aggressive play for that specific market right now.
Oh, they are. They are targeting enterprise data gravity and data sovereignty head on.
Yeah, they just launched general availability of regional endpoints specifically isolated for the US and the EU. And they're hosting third-party open models now, like GLM 5.2. Plus, they've made this massive physical infrastructure commitment, which is 1 gigawatt of dedicated European compute by 2030.
Which is huge. I mean, for a European enterprise, getting clean EU data residency compliance without having to build your own cluster is highly attractive. But, you really have to look closely at the financial mechanisms behind it.
What do you mean?
Well, to guarantee that capacity, Mistral requires you to commit to multi-year European compute units, or ECUs.
Okay, which locks in your pricing.
It does, but it also locks you into legacy hardware.
Oh, right.
Yeah, if you commit to a 3-year ECU contract today, you're hedging against compute scarcity, sure, but you are betting against hardware innovation.
Because the chips get better every year.
Exactly. When the next generation of inference accelerators inevitably hits the market next year and drops the baseline per token processing cost by, say, another 60%, your enterprise is still paying the premium for last year's silicon.
That is a brutal spot for a CIO to be in. And I mean, even if you accept that hardware risk, the regional isolation isn't exactly foolproof either.
No, it's not.
If a cloud architect doesn't aggressively audit Mistral's Trust Center for subprocessor clauses, they are basically walking into a compliance trap. Like, say your primary EU cluster gets hit with a massive traffic spike and it triggers a fallback processing routine.
Right. You have to ensure the mechanics of that fallback don't accidentally route your workload to a U.S. data center just for overflow capacity.
Because if it does, you just triggered a non-EU data spill.
Which defeats the entire purpose of buying the regional endpoint in the first place.
Exactly. But if regionalization is one approach, Meta is pushing decentralization to its absolute physical limit with MuseGlimmer.
Oh yeah, MuseGlimmer is fascinating.
Right. This is a 30 billion parameter open weight model engineered specifically to run locally on standard consumer hardware like a laptop. But running a model that massive on a laptop requires some serious mechanical trickery.
Oh, for sure.
I read they're using a DFlash-based companion for speculative decoding. Can you explain how that actually works under the hood for us?
Yeah, so speculative decoding is actually brilliant. Instead of forcing the massive 30 billion parameter model to generate every single word one by one,
Which would just melt my laptop.
exactly, it would instantly bottleneck a laptop's memory bandwidth. So instead, you run a tiny, highly efficient draft model alongside it. The small model rapidly guesses the next sequence of tokens, and the massive 30 billion parameter model simply verifies those guesses simultaneously in parallel.
Oh, that's clever. And tying it to DFlash means they can rapidly swap the model weights in and out of the laptop's flash storage without just totally maxing out the active RAM.
Right, it's highly, highly efficient.
It is, but as a security architect, I have to throw a massive red flag here.
Let's hear it.
We are granting a local 30 billion parameter model persistent file access and tool calling execution rights directly on a developer's machine, all just to save on cloud API latency. I
Well,
mean, aren't we completely abandoning cloud data loss prevention here? Hasn't this just turned every single developer laptop into an unmonitored attack surface?
we absolutely are. You're spot on. For a decade, the enterprise security perimeter was defined by keeping the data and the processing walled off in the cloud.
Right, keep it centralized.
But by pulling agentic reasoning and persistent tool access down to the local endpoint, the threat vector shifts entirely. Like, consider the mechanics of local prompt injection.
Okay, how would that work?
Well, if a local agent is continuously scanning a developer's repository for context, right? And an attacker slips a malicious hidden instruction into an open source library within that repo.
The local agent reads it?
Yes. And because that agent already has local file system permissions to execute code, it triggers the payload directly on the laptop.
Wow.
It is a complete endpoint security nightmare disguised as a developer efficiency win.
That is terrifying. Okay, so pushing models to the edge is dangerous. But on the flip side, if your massive enterprise data lake is already sitting in the cloud, moving the models locally isn't really an option anyway, right? Just because of data gravity.
Right, moving petabytes of data down to a laptop doesn't work.
No. So you have to pull the data into the model's perimeter at machine speeds. And that brings us to how the underlying cloud architecture is fundamentally mutating to support this. Because Google's BigQuery data transfer service just rolled out some wild enhancements to eliminate these bottlenecks.
They really are aggressively flattening the entire data pipeline.
Yeah, they introduced zero-cost ingestion for major cloud storage sources, native replication for PostgreSQL, MySQL, and Snowflake, and this is the big one. They added a remote model context protocol, or MCP server preview.
Yeah, the MCP server is key.
To visualize this, it's almost like hooking a high-speed industrial vacuum directly to your data lake. You're just sucking transactional schema straight into BigQuery and entirely bypassing the slow, expensive third-party ELT vendor filters that used to sit in the middle.
Right. Mechanically, the remote MCP server acts as this direct bridge. It allows your AI agents to query that raw data while still inheriting your existing IAM and row-level security.
That sounds great.
It does, but let's extend your vacuum metaphor for a second, because there is a severe architectural consequence here. When you bypass those ELT filters, the dirt doesn't just disappear.
It just ends up in your vacuum bag.
Exactly. You still have to clean the data before the model can safely reason over it.
Hmm.
If you dump raw transactional schemas directly into BigQuery without doing immediate dataset level masking at the ingestion layer,
You just push all of your data sanitization downstream.
precisely. You save money by skipping the ingestion pipeline tools up front, sure, but you will pay an absolute premium in BigQuery compute slots to sanitize and transform that raw data post-ingestion.
So you're basically trading ingestion latency for a downstream compute tax.
It's the classic cloud shell game. You save over here, you pay over there.
Right. And AWS is tackling this machine speed architecture from a slightly different angle with Amazon Aurora DSQL. They just published the details on their active connection isolated control plane.
Which is really interesting.
It is, because instead of funneling all database traffic through a primary routing node, every single connection executes inside its own isolated Firecracker micro VM.
Which is a staggering departure from traditional relational database architecture.
Totally, because mathematically, it eliminates head node failovers. Like, if a physical server dies, the entire database doesn't just hang while it scrambles to elect a new master node.
Right, only the specific micro VM connections on that dead hardware are severed.
Exactly, and the client application just instantly reconnects to an active micro VM running somewhere else.
But If AWS is enforcing multi-region static stability by sharding the state across that many isolated micro-VMs, the laws of physics dictate a pretty massive trade-off.
You lose your microsecond local reads?
Precisely. You cannot distribute data that aggressively without sacrificing your single-node memory cache. Furthermore, you lose synchronous traditional foreign key constraints.
Because it's too distributed.
Right. The system is prioritizing planetary scale resilience over localized monolithic speed, so cloud architects can no longer rely on a single lightning-fast database instance. They are now forced to design their application logic around predictable, distributed network latency.
That makes a lot of sense for databases, but what happens when the orchestration layer itself needs to scale at machine speeds? Like Amazon EKS is now actually allowing users to directly configure core Kubernetes control plane flags on managed clusters.
Yeah, that surprised a lot of people.
I mean, we're talking about exposing kube app server and kube scheduler configurations. Why would an enterprise pay AWS for a managed service if they have to pop the hood and tweak the core engine flags themselves?
Well, it's because the default generic settings of a managed service stridently break down under the weight of AI workloads.
Really? How so?
Imagine an agentic workflow that suddenly needs to spawn, 5,000 pods in a single second just to parallelize a massive data processing task.
Yeah.
The default API rate limits that are hard-coded into a managed EKS cluster will view that as a DDoS attack and throttle it instantly.
So giving access to those flags allows engineers to build custom rate limits that can actually handle machine speed scaling.
It's a necessity for survival at this scale. But, and this is crucial, exposing the kube app server flags is playing with the core nervous system of your cluster.
It sounds risky.
It's incredibly risky. If an engineer manually tweaks those flags without implementing incredibly strict infrastructure as code guardrails, they can accidentally bypass default authentication webhooks or just cause complete control plane instability.
Okay, so look at the reality we've just mapped out here. We've opened our APIs to autonomous loops. We've given local models persistent file access. We are dumping raw data directly into analytical engines. And we've unlocked the core nervous system of our Kubernetes clusters. I mean, it is no surprise whatsoever that the cybersecurity perimeter is currently ablaze.
Oh, it's completely on fire. The human element is barely relevant to the perimeter anymore.
Yeah, the numbers definitely back that up. The Cloud Security Alliance 2026 report just dropped a terrifying statistic. They found that machine identities now outnumber human identities 100 to 1.
100 to 1.
Yeah. Basic human authentication isn't the primary security problem anymore. The problem is post-trust session binding and governing what these agents are actually authorized to do once they are inside the network.
Absolutely. If you are managing CI/CD pipelines right now, look at the mechanics of the Team PCP attack on the Little M library. I mean, this is what a 100 to 1 threat landscape actually looks like in practice.
Right, that happened in March, right. Over just a 40-minute window, attackers deployed the Santillo-CK malware into the supply chain.
Yep, 40 minutes was all it took.
It escalated to root on the CI/CD runners, but it didn't just, steal local files. It actually attached itself to the process memory and actively scraped cloud keys, Kubernetes service account tokens, and masked GitHub Actions secrets directly out of the active RAM.
And that 40-minute window exposed 434,000 pipelines.
Unbelievable.
And here is the brutal reality for security architects right now. Patching the code or deleting the malicious package after the fact accomplishes absolutely nothing.
Because the ambient permissions were already exploited.
Exactly. The instance metadata keys and repository tokens were pulled directly from memory. They are out in the wild, and they are usable indefinitely.
So what do you do?
When you have build environments running complex AI dependencies with broad ambient permissions, you basically have to assume the ephemeral runner is compromised. The microsecond a third-party package executes. Immediate cryptographic credential rotation and absolute network isolation for those runners is the only viable fix.
So we have adversaries weaponizing the supply chain. Meanwhile, we have organizations actively building models designed to generate those very exploits.
Right, like OpenAI's Daybreak.
Yes, OpenAI launched this dual-tier access program called Daybreak. Daybreak Blue focuses on defense, but Daybreak Red introduces the GPT 5.6 cyber model.
Which is just wild to me.
It's literally an AI physically designed to bypass standard safety guardrails so it can generate functional chained exploits in 0 days for sanctioned enterprise red teams. I mean, we are handing a localized, unchained 0-day generator to corporate developers. How do we deploy that without instantly compromising our own networks?
Well, deploying a tool like GPT 5.6 Cyber requires an entirely new operational paradigm. You cannot just grant access to a developer's corporate identity like a normal app. Execution must be strictly isolated within ephemeral, zero-trust sandboxes. And authorization to even prompt the model requires physical hardware security keys to cryptographically verify the user's presence.
Oh, I see. So if a developer session token is stolen, the attacker still can't trigger the model remotely without having the physical hardware key plugged in.
Exactly.
Yeah.
And you must implement automated tool call reviews with physical circuit breakers, because you have to ensure that a compromised identity cannot launch a local automated exploitation loop that just moves laterally through your environment at machine speed.
It really all comes down to managing boundaries, which I guess is why Microsoft just pushed intra-tenant governance into general availability. It provides centralized controls to discover and restrict shadow B2B tenant creation across an enterprise.
Yeah, because when you have 100 machine identities for every single human, shadow infrastructure doesn't take days to spin up anymore.
No, it spins up in milliseconds via API.
It's exactly. Centralizing boundary controls is really the only way to stop rogue agents or, frankly, overzealous developers from quietly opening unmonitored external connections to third-party services.
But dropping a blanket restriction policy carries a massive operational risk, doesn't it? Like, if an IT team enforces strict B2B tenant restrictions without deeply mapping their existing machine-to-machine traffic dependencies first, they will instantly break complex, cross-company API workflows overnight.
Oh, they absolutely will. You have to understand the traffic before you drop the blast doors. It requires an incredible amount of systemic visibility.
It really does. So let's synthesize this entire picture for us. We are building these incredible automated reasoning systems capable of proving math theories that humans haven't even cracked. But we are deploying them into mutated cloud environments where identity perimeters have completely blurred.
Right.
Financial guardrails are easily bypassed by recursive loops, and the attack surface has fundamentally shifted away from the centralized cloud perimeter directly to the local developer endpoint and the CI/CD pipeline memory state.
The fundamental role of the cloud architect has completely evolved. We are no longer just builders provisioning resources. We are governors of autonomous machine behavior.
That is a profound way to look at it. For you listening, if you are navigating this shift and want to stay ahead of the curve, for more deep dives into cloud security and AI insights, make sure you follow the show Cloud and Cybersecurity News on Spotify or Apple Podcasts. We covered a massive amount of technical ground today, but I want to leave you with a final thought to mull over as you look at your own infrastructure diagrams.
Yeah, think about this. If machine identities truly outnumber humans 100 to 1, and AI models are now autonomously writing, reviewing, deploying, and executing their own code, are we as cloud architects actually managing our infrastructure anymore? Or are we simply negotiating with the agents that do?
It certainly makes you look at that static city grid a bit differently, doesn't it? The traffic isn't just driving itself anymore, it's actively paving the roads while we watch. Until next time.